Hello, my name is Lana Van Note, and today I'll be speaking about plastic. Plastic is a toxic, ubiquitous endocrine disruptor that accumulates at a rate of 8 million metric tons every year, leading to pictures like this. When was the last time you threw out a plastic water bottle? Do you even remember the last time you did? Out of sight, out of mind, right? Well, unfortunately, not for people whose backyards have been turned into fields of plastic debris. Being a Jersey Shore resident, I've seen firsthand the beginnings of this kind of deposition on the beach, which has prompted me to dedicate my research to fighting against the plastic pollution problem. 7 years of research have shown plastic's low biodegradability and high toxicity to micro and macroorganisms alike. This has prompted me to create my own sustainable plastic alternative. Bioplastics, or plastics composed of at least 20% renewable materials, are currently seen as the leading solution to plastic pollution. The issues of recycling, such as a very low percentage of products actually eligible and undergoing the process, and biodegradable plastics, or plastics that merely break down into smaller pieces and contribute to microplastic pollution rather than degrading into smaller, non-toxic particles, are eliminated. So the key part of this research is creating a plastic with a base material that is sustainable. So I chose bamboo. Utilizing a food source is not a good idea due to limiting the amount of food availability, as well as increasing the amount of overuse of fertilizer and excessive genetic modification. Bamboo is an inexpensive and fast-growing product that contains tannins, which are antibacterial particles that form complexes of strong bonds with carbohydrates. So the carbohydrate I selected was chitin. I used chitosan derived from chitin. So chitin is an abundant polysaccharide that's found in the exoskeletons of crustaceans, shellfish, and insects. So these two materials would combine to form a complex of strong bonds that would hopefully make my bioplastic stronger. And I also added agar-agar, a derivative of seaweed, and I also included glycerin, acetic acid, and distilled water to make sure that the solution would be of the right acidity for the complex of strong bonds to form. So this research was divided into two main parts, the first being the synthesis and formulation of the bioplastic, and the second being the final bioplastic's comparison to polyethylene, a petroleum-based film that is commonly used in plastic bags. So first off, I used the solution casting method to create my bioplastic, which involved combining all of the constituents over heat and letting them sit and set in silicone molds. So here's the flow chart that basically demonstrates what I did throughout the trial and error process to arrive at my final formula. Over 60 different formulas were created over the course of 9 months, and I made tweaks based on the film's condition. So for example, if the film was too brittle, I found that glycerin was largely responsible for the film's brittleness and flexibility, so I would increase the amount of glycerin to make sure that the film did not crack. And this process underwent for every constituent in the formula until the best combination was found. So once I had my 60 bioplastics, I narrowed them down to 9 final formulas based on just observation. Then I applied 3 preliminary tests, first being strength testing, found by a homemade tensile strength test, fatigue testing using 90-degree bilateral flexes in sequence, and then transparency testing using UV spectrophotometry. And transparency was included because it is important when creating an aesthetically pleasing product for the market. So to the left is one of the grading scales I used to assign points to each of the films after the preliminary tests. So the film that had the largest total would be the final formula out of the 9 that I was testing. To the right is a table showing the final 9 formulas, the main variables that were changed, and also the results from the preliminary and final tests. So trial 9 was the final formula because it did have the highest total of 8 points. So this film was moved on to compare against polyethylene. So the main tests that I used were biodegradation testing by placing 10 samples of each film in simulated landfill soil for 144 hours, after which an FTIR analysis was used to find the biodegradation rate. A water absorption test was performed by submerging 15 samples of each type of film in distilled water for a period of 1 to 60 minutes, and then reweighing them using an analytical balance to find the difference in weight. Finally, a solubility test was performed by measuring the concentration of tannins in the final solution after the water absorption testing using colorimetry. So these tests were selected mainly because they're the two main ways a plastic product can be disposed. It can be thrown in the soil or in the water, and I want to see how my bioplastic performed in those two scenarios. So here is the FTIR spectra of the biodegraded bioplastic samples. I analyzed different peaks in the FTIR spectra to determine the final biodegradation rates or weight loss. So the three grayed out areas are the peaks I analyzed, labeled 1, 2, and 3. The blue line represents the control, which was an unbiodegradated sample, and the green line represents a biodegraded sample. So I compared the ratio of the two peaks in order to find the biodegradation rate, which was 22% for the bioplastic samples and about 2% for the polyethylene samples, a difference that was insignificant according to a t-test. So the reason for this difference is likely due to this peak right here. This peak is representative of carbon-carbon double bonds, long chains of them. And these long chains of these bonds are not normally found in nature, meaning that microorganisms are not equipped with the pathways to degrade these long chains of bonds, which is why polyethylene is very indestructible, very hard to break down, and very long-lasting. So for the water absorption and solubility tests, the polyethylene samples didn't absorb almost any water or dissolve at all throughout the 1 to 60 minute period. However, the bioplastic samples saw a rapid increase in water absorption and solubility between minutes 0 and 5. After which, the water absorption and solubility tended to even out to ultimately reach 200% water absorption and 18% solubility by the 60-minute mark. Next, you can see the FTIR spectra of the water absorbed samples, and there was also a significant difference found between these samples and the polyethylene samples. And this difference was likely due to this peak right here, which is indicative of hydrogen bonding. So hydrogen bonding is a polar bond, and when a polar substance, a polar solute, is dissolved in a polar solvent, dissolution will occur according to the chemistry principle like dissolves like. Therefore, it's reasonable that these trials dissolved while the polyethylene samples did not. Next, I have a cost analysis of each of the types of films just to see if they would be comparable in price. So for the polyethylene samples, there's about a 0.2 of a difference between the polyethylene and bioplastic samples, which is pretty close, and this gap is closed even further when you consider the cost of landfill maintenance and recycling for polyethylene. So to conclude, the hypothesis was partially supported in that the bioplastic did degrade faster than polyethylene, though it wasn't a significant difference. But when you consider the bioplastic's biodegradation rate compared to other types of polyethylene, such as high-density polyethylene, the biodegradation rate is 5,700 times faster than those tougher products. The hypothesis was rejected in that the water absorption and solubility was much higher than initially predicted. And these properties are very good when trying to create a product that degrades quickly and is safe for the environment, but it isn't too great when you're trying to make a product that is able to withstand use. So let's review what this project accomplished. So first, a problem was identified, the plastic problem, and then a solution was developed, creating a bioplastic. After that, a prototype was created, and it entered the process of trial and error, correcting different things that were found to be not favorable, and this process was repeated 60 times. And of course, throughout this process, the original mission was kept in mind, combating plastic's high biodegradability. So what comes next is optimizing the film's properties. Creating a seal on the outside is something that I'm looking to do to combat that high biodegradability in water absorption and solubility. Creating one that is high in tannins would be favorable because tannins, their antifungal and antibacterial properties, would combat the bacteria that are degrading those products rapidly. Therefore, the product would be able to withstand use, not have to worry about breaking down too rapidly, but then able to undergo this rapid biodegradation that was found in this experiment after that point once it's disposed of. Next, there's the application to real-life scenarios. So creating this as a wrapping for consumables and testing to see what is the effect on the food. Is it effective? Is it doing its job, and will it actually break down like it was predicted in this experiment? Once and only once that is done, then it can be presented to the market as a legitimate, sustainable plastic alternative. Thank you very much for listening to this presentation, and I hope you enjoyed.